And it's got a very, very nice intuitive description about what is regression, when the model is wrong, and all the things we've kind of talked about. So if you want to read more about it, that's just something you can look up. All right, so let's talk about the high-dimensional case. D is bigger than n. We can't use least squares. So I mentioned quickly at the end ridge regression, but let's talk about sparse methods. Oh, you're lucky that the lock didn't work. I tried to lock you out. All right, you're all coming in, but you know that the door is supposed to be locked now. You're not even listening to me. All right, let's try again. Oh, wait a second. There it goes. You guys really lucked out. OK. So to get a sparse regressor, there's really, I guess, two main methods, which would be some sort of greedy regression or some sort of L1 penalization, like the lasso. So let's just talk a little bit about greedy regression. This is actually much harder to analyze than L1 regression. And I'm just going to mention eventually what I consider to be one of the best results that's known. The proof of this result is actually in the appendix to these notes. It's quite long and complicated, much more difficult, I think, than the lasso stuff. And so, in statistics, we call this forward stepwise regression. I think in signal processing, maybe it's called, is that orthogonal matching pursuit or something like that? It goes by different names. But basically, how does it work? So I'm going to take my y, and I've got these covariates, x1 to xd, and I've got the data here. So the way it's usually done is we just do a one-dimensional regression of y on x, one-dimensional regression of y on x2, one-dimensional regression of y on x2. So you do a bunch of one-dimensional regressions. Let's say everything's normalized so that the columns of x have everything's normalized to be 1. So that to have mean 1. Sorry, the sum of the squares, the average sum of squares here is 1. So in other words, finding the best regressor, that is finding the thing that's the best one-dimensional regression, is really just finding which thing is most correlated, right, with x. Just saying, what's the correlation between y and x1, y and x2, and you pick the best one. So suppose that's the third one. So now you create a bag of variables that you've selected so far. Let's say it's 3. And so we remove, this was x3 here. We just remove that. Now we regress y on x3. So, and again, I'm going to just assume that the coefficient is, the intercept is already included. Or if you want, remove the mean of y. So we're going to do a regression, a least squares regression, and we'll get some sort of beta hat 3 x3. And now we take what's not accounted for in the regression. So we take the residuals. People are trying to get in. That's what's left over after the linear regression. And now we just repeat. I take the residuals from that regression, and I regress, and I just take the correlation on x1, x2, x4. So find the best one. Let's say it's 17. So now I add that. Now it's important in the usual version of this, there's different ways of doing this. The usual version is you don't use the old regression. You start again, and you regress y on both of these. So you do least squares on these two. The best linear combination of these two. You get the residuals, and you repeat. Okay, so that's the usual version of forward stepwise regression. There's other versions called L2 boosting and various variations of it. There's continuous versions of it, and so on. But basically, you just keep doing linear regression on the variables you selected so far, get the residuals, find the next best variable. And you can see why it's difficult to analyze, because everything you do depends on the last step. And this is probably, I would say this is the oldest method for doing sparse regression. So when I was a student, we didn't have, no one knew anything about convexity and lasso and stuff like that. It hadn't been invented yet. this was the method. This was what we did. When you analyzed high-dimensional data, or even moderate dimensional data, you did forward stepwise regression. That was it. And the nice thing about it, of course, is very easy to program, even though we're not solving a convex problem, but it's very easy to program. It's very easy to do it. Now, you have to, of course, decide how many variables to enter. And I guess we'll talk about, we haven't really talked about cross-validation. When are we going to talk about cross-validation in detail? But we'll be talking about cross-validation in detail at some point, I guess during non-parametric regression and also during concentration of measure. But for now, just imagine you keep some held-out data, and you just see how well you can predict the held-out data. And so we would typically, and this is not the only way to do it, but we would look at the estimated, so this would be the cross-validation error versus the number of things in the model. Let's call that k. And then you would choose the number of variables by minimizing the observed prediction error on the held-out data, the cross-validation error. And again, there's different versions of this. There's leave one out, cross-validation, so on. Let's not worry too much about that at the moment. So there's a tuning parameter, which is how many variables to include. But the whole process is easy, right? You just fit the first variable, second variable, third variable, where you're doing a least squares regression every time. We're estimating the regression error, and now finally this is telling you, okay, let's pick 10 variables, and that'll be your final model. Okay, so I'm sure you've all seen some version of this before under different names. So that's called greedy regression, forward stepwise regression, whatever. Okay, is the procedure is clear? Any questions about the actual procedure? Okay. There's a lot of caveats here. It would be a big mistake to do this and then start doing like tests of significance and things like that on these data, because you've greedily chosen things that are highly correlated with y. So you would overstate the significance of the beta hats. So how to do inference and all that, remember I said, is a whole different question. Right now we're just talking about prediction. All right. What can we say theoretically about this? There's just quite a bit of work about this, but it's, like I say, it's pretty nasty to analyze. But let me just mention a few things. I won't go into great detail. There's a lot of details in the notes about this that I don't think we'll cover in class, but I do want to mention a little bit of stuff that's known about this. What I'm working up to is the following fact, that it's going to turn out under fairly general conditions that if I did forward stepwise regression and I look at the predictive risk I get and I compare that to some optimal thing, which I'll describe in a minute, that we're going to see that this is something like 1 over the square root of n under fairly general conditions. Now, people often call this the slow rate because there's other results in regression. Don't forget, these are squared errors, right? Squared prediction errors. There are a lot of results that get 1 over n. In fact, the last results I gave you last class, there was things of order 1 over n. This is 1 over, so back on the original scale, if I took the square root of this, this would be like 1 over n to the 1/4. So people call that the bad rate, but it's not really bad. First of all, it's dimension independent, which is pretty amazing. Although we're not talking about estimating the true regression function, we're talking about getting close to some oracle, which I'll explain in a minute. But it's also minimax. You can't beat this under general conditions. You can beat it, though, if you add more assumptions. So let me just give you an inkling of how these things are proved. Again, I don't want to, we could spend like weeks doing all the details. So there's some beautiful work by this guy, Temlikov. And this is from the applied math literature, the approximation literature. And then it was recently, well, not recently now, I guess it was quite a while ago, combined with some statistical work by Andrew Barron and Ron DeVore that gets this result. So I just want to kind of give you a sense for what it's all about. Is they start by saying, forget about regression and forget about data. Let's just think about it from the point of view of functions. Suppose I just had a function. Let's say f is a function in some space. Let's just take the unit interval just to have a concrete thing. So here's the unit interval. I've got some arbitrary function. And what are we doing when we're doing regression? Well, we're trying to predict, but another way to think about it is we're trying to approximate y with a linear combination of the x's. So from the functional point of view, I might ask, how well can I approximate a given function f from by a linear combination of some other functions? That would be like our features. So in this literature, they define these, they call it a dictionary. And the reason why they call it a dictionary as opposed to a basis is because this is not necessarily an orthonormal basis. This is a collection of functions. So this is just some collection of functions. We'll assume these things have finite integral and so on. And I'm asking the question, if I had to approximate f with 10 of these, how well could I do it, and what's the algorithm for doing it? And there's no noise. This is the noise-free version. It's just a purely functional version. So what you could look at is, and this is what, and this also, by the way, is going to show you how sparsity comes into things. It just shows you another aspect of sparsity. Is we define sigma capital NF to be the following quantity. So here's what we're doing. You give me a capital N. That's the size of the model you want to fit. This is where sparsity first enters. I only want to use 10 of these functions to approximate f. So yeah, n is 10. Now what lambda represents is any subset of size 10. So I'm going to take all subsets of this dictionary of size 10. And now what I'm going to do is for every such dictionary, I'm going to look at those 10 functions and look at their span, all the things that can be written as linear combinations. And so I'm just going to take how close can I make f to g, where g is, I take the minimum over the span. In other words, what is that? That's just regression, right? That's just the functional version of regression. I'm minimizing the L2 error between f and all linear combinations of these functions. And then I'm taking the smallest over all possible subsets. So you see it, that's looking NP hard, because I could never really take this. But at any rate, let's define the sigma sub nf. That's just saying that's the error you would make, the L2 error you would make in the best possible approximation using this dictionary. So the cool thing is what Temlikov did is he said, well, let's suppose we just do the functional version of forward stepwise regression. What is that? Well, remember, f is like your data now, only it's a function, right? What I do, I use the same algorithm. I wrote it out again in the notes. I take the correlation between f and sigma 1. Let's again assume everything's normalized so that, like, for example, the integral of f squared is 1, the integral of psi j squared is 1. We can always renormalize things. So in other words, I look at the integral of phi fj. That's just the functional version of what we did in forward stepwise regression of taking correlation. And I do this for every function, and I choose the best one. And that goes into my bucket. And now I take the difference. I take the residual. I regress f on, let's say I pick phi 3. In other words, I find the best coefficient, the best L2 approximation. I minimize f minus this squared. That gives me a beta 3. Now I take the residual and add in the next function. So it's exactly the same as forward stepwise regression, just using functions. And you keep going. And Temlikov proved this very beautiful theorem, which shows the role of sparsity in doing forward stepwise procedures or greedy procedures. This is equation 4 on page 7. And if I look at the residual, and let's define residual here. The residual at time n is just f minus fn, where fn is simply the projection onto the span of the subset that I chose, the best approximating n. So again, this is actually on page 6. The algorithm's written out. I called it orthogonal greedy algorithm. It's just the functional version of forward stepwise regression. And here's the beautiful result. What's left over after n steps, of course, it's going to be decreasing, right? If I keep approximating with more and more and more things, the approximation is going to get better and better and better. But at what rate, and what's going to control it? And here's the answer. There's two things. The first thing is that for this greedy procedure, the rate at which we approximate the function better and better and better is 1 over the square root of the number of things that we've included so far. And what the heck is this thing? This is not the usual L1 norm. This is sort of where sparsity comes in. I should have said for this result, for the moment, we're assuming, because there's countably many, I'm going to assume that f can be written as some linear combination. We'll drop that assumption in a minute. So f can be written as a linear combination of these things. But it's not an orthonormal basis, so it may not be unique. There may be many ways to expand f. So you could write f as an infinite combination of the phi's. Okay. And what we're going to do is take the L1 norm of these betas and take the smallest such L1 norm over all possible representations. Okay, so expand f. There might be many ways of doing it. Once you expand it, take the L1 norm of these betas and find the minimal L1 norm. So that's what's defined there on page 6. That's what goes here. That's kind of a measure of the sparsity of the function in this dictionary. If I can represent this function well with a small number of guys, then this quantity will be small. And so this is showing you that this greedy procedure is approximating things very, very quickly. In fact, even if f is not in the span of these functions, then what happens is that the residual can still be written. You just take the closest function h to f. Let's call h the closest function. And you get basically the same result. And this is on the squared scale, so that's why there's an n here. There's going to be an error due to the fact that the closest guy in the linear span of the dictionary is not equal to f. So that's like the bias you get because the function isn't actually in the class. And then you get a similar result. And again, it depends on the sparsity of the best approximating function. You can think of that as a measure of the sparsity. The nice thing about these two results is the proofs are, I almost considered doing them in class, but I decided against it. But the proofs, I put them there. They're complete. They're not very long. Very elegant, simple proofs just using properties of norms and things like that. So let's summarize. If f can be written as a linear combination, then after n steps, the error goes down like n plus 1, and there's a constant which measures, in some sense, what's the best sparse representation in that dictionary. If it's not in there, there's going to be a bias term. But if you think of this as the excess risk, this minus what's the closest you can get in that dictionary, it's still going down like that. And this part's the easy part of greedy regression. The hard part is this. How do I convert this into a statement about forward stepwise regression? Well, what's the difference? There's two big differences. We're dealing with randomness now. Things are random variables and so on, so things get a little bit more complicated. And then there's a technical issue, which is that when you have data, we're not dealing with norms. Like, we're never really dealing with norms like this. We're always dealing with database things that would look more like this. So what's going to happen is, because of the variability introduced here, there's going to be a bias variance trade-off. And in particular, there's going to be some work to show that these things approximate these things with high probability. And that's going to, how do they do that? Well, using concentration of measure, which is stuff we'll talk about later in the course. So this is where it gets, unfortunately, a little bit nasty. And so I'm just going to state the result. And this is theorem 10. And this is the result from Barron, Cohen, Dauman, and DeVore, 2008. You can look up the result if you want. And I actually have the proof of this theorem in the appendix, but it's quite long and technical. But it's really taking Temlikov's result and accounting for the fact that now we have random variables. So there isn't just bias in some sense, there's also variance. And what they show is the following thing. If I take an arbitrary function minus its linear approximation based on n steps of forward stepwise, n in this case turns out to be square root of n. That's not what you would use in practice. In practice, we would use cross-validation or something like that. But theoretically, that's the optimal choice in general. And so what we get is that f minus f hat n turns out to be, you can rewrite this as basically f minus the best linear approximation, which is what we're doing. Like from our point of view in regression, we're not assuming the truth is linear, but we're always trying to find the best linear approximations. That's what I mean by f star. And the error, again, is this. This is what's called, again, the slow rate. So that was a little bit vague because I didn't go through the details of how you go from Temlikov's result to the statistical result. It's a long route. But I want to put it up there because I think it's pretty interesting that there's basically no assumptions in this theorem. The data are assumed to be IID. Their proof actually assumes that the probability measure is supported on a compact set. People often make that assumption just to avoid a lot of technicalities. You could eliminate that at the expense of a lot more work. So again, this is on the squared scale. So if I took the square root of this, if I went to the non-squared scale, this would be like 1 over n to the 1/4. So it sounds slow to a lot of people, n to the 1/4. I don't know if it sounds slow to you or not, but some people sound slow. And it is kind of slow, but it's fast, too, because it says nothing about the dimension. There's no assumptions. We're not assuming the function is linear or anything like that. And in fact, there's a proof that this is minimax optimal, that without further assumptions, you can't do faster than n to the 1/4. And we're going to see the same is true of the lasso. The most general result of the lasso gets exactly the same rate. But then, if you're willing to introduce more assumptions, you can do much better than that. In fact, I'm going to move. That's all I really want to say about greedy regression. I'm going to move on to the lasso. Are there any questions? Yeah.
How do you construct the function basis?
How do you construct the basis? Well, that's a good question. So in if we were trying to think about this as non-parametric regression, how we would choose a basis becomes an important question. But here I'm thinking about this as what we're actually not doing. I've written it functionally, but we're actually just trying to write in a very abstract form what we're doing when we do greedy regression. The x's are given to us. So we don't construct the basis. You're given y, and you're given the features, x1 to xd. That dictionary is given to you. That's just the data you collect. So we're not constructing it. The question about function approximation, how to choose a basis, of course, is an interesting question, but that's a bit different than what we're talking about. I'm just talking about linear regression. You get a bunch of y's and x's. How good can we do by doing forward stepwise regression? You don't get any choice in the features, in other words. So it's an easy algorithm, forward stepwise, but it's surprisingly difficult to analyze it theoretically. And I must say, in terms of, we're going to now do the lasso. And so what works better in practice, forward stepwise regression or the lasso? For years, I used to say, I never find any difference. And Ryan would tell me I'm crazy, that lasso tends to work better. I think I'm now a convert. I think I've seen a lot of cases where, well, there's a lot of examples where what you do with forward stepwise and what you do with lasso in predictive error maybe isn't so different. But I think there are cases where forward stepwise can do pretty poorly. It's a very discrete procedure. So, you know, it's not a nice smooth thing. And generally speaking, things that aren't smooth don't often work very well. There are smoothed out versions of forward stepwise regression. which actually link forward stepwise in some sense to the lasso, where instead of adding in a variable, you kind of add in a little bit of a variable at a time. I don't know if we were planning it. Are you going to talk about Lars? Yeah, so that's called Lars, and Ryan will talk about that later in the course. So let's go to the lasso. So before we go to lasso, let's remember, why were we doing forward stepwise? Well, that's just a greedy version of the L0 problem. Remember that if I wanted to do regression, I could, in a high-dimensional problem, I could say, well, what's the best one-variable regression? What's the best two-variable regression? What's the best three-variable regression? In principle, what I would be doing is minimizing the training error subject to only allowing myself to use, say, 10 variables. That was equivalent to, remember, making the L0 norm, which is just not really a norm, but it just counts the number of non-zero variables. Minimize the training error subject to the L0 norm being less than k. And the reason why we went to greedy regression is because we can't do this minimization. It's NP hard. You'd have to search over all subsets of size k. Plus, you'd want to do it for different values of k. So solution one was, well, if I can't search over all possible subsets, let's just do it in a greedy way. And that's how that's why everybody did forward stepwise regression for 30 years or 50 years in regression. It was the only thing we knew how to do. That or ridge regression. But then along came the lasso, and which said, instead, let's relax this. Let's relax the L0 norm to a slightly friendlier norm, the L1 norm. And as you saw in your other courses, things get much easier. Remember that the L1 norm is just this. Now, there's two ways to express L1 regression. Minimize this subject to this condition, or we add it on as a penalty. Probably that's more common. In a sense, they're equivalent, not that you'll get exactly the same answer, but rather that you'll get the same solution path, right? As I vary lambda, I get a sequence of solutions. If I vary to L in the other formulation, I'll get a sequence of solutions, and it's the same sequence of solutions. The exact correspondence between them will depend on the data, but you're going to get the same solutions. And the reason why this is such a good thing to do is because it's convex. Those of you who have taken Ryan's course in convex optimization know then there's all kinds of known stuff about how to optimize this thing. I'm not going to tell you anything about that. But we can optimize this, and we'll get a beta hat, which will depend on lambda. And as we discussed on Tuesday, that's going to be sparse. Many of the beta hats are 0. So it's doing estimation for you and variable selection simultaneously. Okay. So I'm just going to mention, as I said, Ryan's going to talk about this in more detail. I will mention, just want to mention, maybe I'll skip these results. I'll just tell you what's in them, and then get to the third result, which we can prove in about a minute because of the proof that we did on Tuesday. So the hard theorems are here, the theorem 11 and theorem 12. Let me just tell you what they're about. And there's a little bit of controversy about these results. So the first one is about something called sparsistency. Sparsistency is a term that was invented by Pradeep Ravikumar, who's actually now at CMU in the machine learning department. Everybody forgot that he invented the term. It's a very cool term. What does it mean? Here's what it means. Suppose that the true regression function is linear. So suppose y is equal to, and suppose that the true beta is sparse, which means that there's a lot of zeros here. So in that case, we can talk about the support of beta, which is simply the set of j's for which beta j is not equal to, not equal to 0. Those are the non-zero betas. So sparsity, at the very least, means the support is not all of 1 to d. Then we can talk about the lasso estimator. Beta hat also has a support. And what sparsistency means is that the support you want that the support of your estimator is equal to the support of the true beta with probability going to 1. Okay, and what theorem 11 talks about, and I think are you going to do a proof of this later in the course? We might do a proof of this later in the course. Let's see what it says. It says under some conditions, the lasso is sparsistent. Now, this is a very personal thing. I don't really like this result because let's talk about the assumptions. First assumption is that the true model is linear. So I'm already unhappy. I don't know why I would ever believe that. Then you're going to need that the non-zero betas cannot be too close to 0. Obviously, suppose one of the betas was like 0.000000001. How are you going to tell that from 0? You're not, right? So you either have to assume that the betas are 0 or a certain distance from 0. But you can't have everything in between. Anything in between. Which is pretty weird because most of the rest of the field of statistics is concerned about things that are close to 0. There's a whole theory of efficiency and so on we talk about in statistics, which is all concerned about what happens when things are very close to 0 but not equal to 0. But the worst thing is that, it's pretty clear, if you've ever done regression in practice, I hope you all have, that real data sets, when you get data, let's suppose I'm studying a disease. I'm going to collect data on people. I'm going to collect their age, their blood pressure, everything I can think of. People try to collect everything they can think of, especially in our era of big data. You collect everything. Maybe I collect all your genes. I collect everything. Things are correlated all over the place, right? It's very typical that data are very collinear, which means with all those variables, you're going to find things that are very highly correlated. And you can't tell them apart. So let's suppose that, think of our design matrix, all these features. Let's suppose that x1 and x2 are very, very highly correlated, which is going to happen in practice. How am I going to tell? Think of the extreme case that they're perfectly correlated, right? I could never tell these two models apart. Suppose the truth was that beta 1 was really important and nothing else mattered. Or suppose it was that beta 2 mattered and nothing else did. If x1 and x2 are perfectly correlated, you can't tell these models apart, right? Because they're surrogates for each other. But even if they're not perfectly correlated, if they're highly correlated, it's basically the same thing. You're never going to be able to tell, is it beta 1 that's 0 and beta 2 is really big or the other way around? So the way this is ruled out are through certain conditions on the design matrix that there's various flavors of these conditions. They're called sometimes restricted eigenvalue conditions, consistency conditions. They go under different names. But they all amount to you can't have too much correlation between the x's. In one way or another, that's the kind of thing that's assumed. So, again, I don't like that because when I took regression as a student, the first thing we learned in class is everything's going to be correlated. That's what we're going to spend the rest of the course dealing with, is the fact that everything's correlated with each other. And so it seems very odd to me to make an assumption like that, but that's me. It's just me. I could be wrong. But on the other hand, I have to say, from a theoretical point of view, if you really want to understand what's going on with the procedure, it's not such a bad idea to make these assumptions, right? If you want to understand something theoretically, sometimes you have to just say, well, let's make these assumptions and study how the procedure behaves. So if we do that theorem later in the course, you'll see there's all these assumptions, linearity, some sort of sparsity, some sort of condition, beta min condition as it's called, some sort of design condition on the design matrix. And under those conditions, you can see some beautiful results that will imply that this is sparsistent. And of course, you also need to choose the lambda carefully. So those results, I think, are actually very useful as long as you keep in mind that they're for theoretical purposes. They're trying to help you understand the procedure. How useful they are in terms of actual practice and data analysis, that's the part that I have some qualms about. But Again, not everybody has different opinions about it. There's a similar theorem right afterwards, which instead of talking about sparsistency, talks about something slightly weaker, but the conditions are not terribly different. But basically, it's not requiring you to get the support right. It's requiring instead just that beta hat minus beta goes to 0 in probability. That's what we called in 705, that's what we called consistency. But it still requires that there be a true linear model, otherwise it's not even clear what that even means. And that's what theorem 12 is about. But let's actually prove theorem 13, which is, remember I proved on Tuesday the result about the prediction error of least squares. Well, the same result basically holds for the lasso. I really love this result. It's very simple. It's very beautiful. And to me, it shows a very strong property of the lasso, and it does so in a completely assumption-free framework. So what do I mean by assumption-free? We're going to assume IID. That is an assumption. I don't want to give you the impression, by the way, that sometimes I say, weak assumptions. Well, IID we assume all the time is a strong assumption. So we're always assuming that unless we say otherwise. And again, for technical convenience, we're going to assume bounded support. That one's not really necessary, again, but it's mostly for mathematical convenience. And what's the result? The result's going to say something like we said on Tuesday. So let's go through the result, and the proof's almost the same. It's just a matter of keeping track of things. And again, it shows you, one thing I like about this is it shows you how the L1 norm in some sense pops up naturally. This result is proved in this paper that I've referenced here by Greenstein and Brithoff, although the truth is they're actually generalizing a result, which originally in a paper, I forgot to put the reference there, by, what's those guys' names? Nemirovsky, do you remember? Two Russian guys. Juditsky and Nemirovsky. So I'm sorry I forgot to put that reference. They were really ahead of their time. And here's what it says. Let's think about, we're going to assume again, we're doing the lasso, but we're not going to assume anything about the design. We're not going to assume the model's even linear. So what is it we're actually doing when we do the lasso? So it's good to clarify the population version and the sample version. Well, the sample version is what? It's minimizing, again, we can write it in two forms. For this result, I'm going to write it in the constrained minimization form. So we're minimizing the training error subject to the L1 norm has a constraint. We're just doing that constrained minimization. So I think it's natural to think of what is it we're estimating? Well, we're trying to estimate, in some sense, the best sparse linear predictor. When I did least squares, I said what we were doing when we were doing least squares is we were just estimating the best linear predictor. Now we're trying to estimate the best sparse linear predictor, where sparsity is in the L1 norm. Maybe I should just, in a minute, I'm going to go back and remind you why it's good to think of L1 norm as measuring sparsity. You guys did that, and do you need that? In 701, something you know L1 norm is related to sparsity? Okay, so I won't do that. All right, so, well, this is just an empirical average. So if we call the minimizer of this the lasso estimator, beta hat, a natural population analog is to say, well, I'm minimizing the expected value of this subject to the same restriction. This is the population lasso estimator, so I'll call that beta star again. And again, just think of it as, in some sense, the best sparse linear predictor. And what I really want to know is, how well can I predict using this compared to how well can I predict using this? And what we saw on Tuesday was, to prove that, all we have to do is, in general, relate, what did I call it? I hope I'm using the same notation. If I've switched letters here, I apologize. remember what we did to show that beta hat predicts almost as well as beta star. We first just showed that the training error and the true error are close. We showed those were epsilon away with high probability. We did that with Hoeffding's inequality and the union bound. The only thing that changes here is we have to bring the L1 bound into that, but that's going to come up very naturally. Because everything's bounded, if I was only worried about one beta, we have a sample average and its mean, so it would follow immediately by Hoeffding's inequality that this is close to this with high probability. But as usual, what we're concerned about is uniformity, the soup over all betas. But we get to use this constraint. And what we did last time, I'm not going to do it again, was, remember I rewrote the risk in terms of the z's, and I expressed these as a quadratic form, and I took the difference. So all I'm going to do is not throw away something that I threw away last time, which was, I'll just remind you what it was. It was r hat of beta minus r of beta we saw was less than or equal to the L1 norm of beta squared times delta n. Actually, there was an extra -1 in there, but I'll just ignore that. That's not a big deal. And delta n, remember, was the maximum difference between, I think I called it lambda hat, right? Remember, lambda was the expected value of z. So remember that? In that proof we did on Tuesday, the first step was we just took the difference of these two things and saw this was less than the L1 norm squared times this maximum difference. And this we know we can bound every term by Hoeffding's inequality, and we can bound the maximum by the union bound. That's what we did. The only thing is I threw this away last time. I called this a constant. But now we got to keep track of it, but that's easy. We're just doing a restricted minimization over the set. So everything's being restricted to this set. So this is less than or equal to L squared delta n. And just to remind you, I think we showed with Hoeffding's inequality and the union bound, this is less than or equal to d squared times, this is the number of things in the matrix, this is Hoeffding's inequality, and this is the L. It's exactly the same proof as last time, except I kept track of it. Now I'm keeping track of these two things. And what we concluded, remember, was that therefore, with very high probability, except on a set of probability this, we have that these two things are close, and from that we did that simple argument that therefore r of beta hat was less than r of beta star plus 2 epsilon. What we want to make sure, though, is that this is a small number. Let's say delta, and solve for epsilon. And if I just solve for delta there, what we conclude is that with probability at least 1 minus delta, we get that the predictive risk of the lasso is less than or equal to the predictive risk of the best sparse linear predictor plus, and when I solve for epsilon and put it in here and put it in there, let me show you what you get. You get 16, it's a bunch of, let's not worry too much about the constants, I guess. Let's just get the main terms here. It's basically L to the 4th over n. Let's write it like this. This is the main terms. This is very revealing. This is, to me, sort of explaining why the lasso works. So first of all, we see the L1 norm naturally came into it. And as you get more data, of course, you're changing the regularization parameter. And this is telling you something about how that can change. Because L to the 4th If we're going to let L increase with the data, for example, with the sample size, it better go no faster than n. Otherwise, this is not going to go to 0. But the most important thing is, how does dimension enter into it? Log d. It's one of those beautiful things that we started off with a high dimensional problem, but now the dimension has become only a logarithmic problem. We tend to think of logarithms as small, not so important things, so that's good. It's a log d. If it was like, a polynomial d, we'd have a problem. And the beauty of this proof, if you've forgotten the details from the last proof, don't worry, it's all there on page 12. The proof's half a page long. So the beauty of this proof is very simple, and there are essentially no assumptions again. Right, we're not assuming the true model is linear. We're not assuming that the design matrix satisfies a minimum, some sort of eigenvalue condition, nothing like that. Okay. Now, okay, good. So that's a brief reminder and maybe a little bit new stuff about the lasso, which we'll come back to later in the course. All right. Any questions? I do want to point something out, though, that, oh, yeah.
I'm a little confused about the N2 code. So what does that indicate exactly that if you have a higher parameter, there's a larger error?
Right. So let's draw a picture of it. I'm minimizing over an L1 ball. And I'm finding there's a best sparse linear predictor, and then there's my estimate of it. And that's just saying, if I do that over a bigger set, there's going to be a bigger error between those two things. It's kind of taking the role of the dimension in some sense, the complexity. Okay. Let me just say another word about how are we doing for time, because I was hoping to also do the whole review of linear classification. That'll be quicker, though. All right, because I did want to mention something about a kind of an interesting fact about sparsity. I think it's good I like to throw in these little results that just sort of make you think a bit. And so sparsity is a very, very convenient, good thing in some sense. As we talked about, having a sparse predictor is very convenient. Sparsistency, which is if something is really truly sparse and you want to find the non-zeros, also seems like a good thing, and it may very well be. But there is a price to pay for sparsistency, which is that it can actually create a high estimation risk in general. And this relates to what we talked about in 705 when we talked about minimax risk. And again, we're going to talk about it in this course too. So this is at the bottom of page 12. I just want to show you a simple calculation. It's a theorem by Lieb and Pocher, or Pacher. I don't know how you say that. But it's actually an old result recast, because it's something called the Hodges phenomenon, which has been known in statistics for a long time. But the point is just to show that if you do want a sparse-listed estimator, so I want something that really finds the non-zero elements, the things that are close to sparse but not quite sparse will typically have high risk. They're going to have bad mean squared error. And this is just a proof of that fact, and it's very simple. It's so simple, I think, yeah, let's go through it. It's 4 lines long. So here's the idea. Let's suppose we have a beta hat. And they actually they only are even talking about something weaker, which is called weak sparsistency, which is simply that the probability, let's say under the true beta, that the indicator function equals 1. And they write it like this, that the indicator what is this saying? They call it weak sparsistency because whoops, that's not right. This is a typo here. This should be not equal to 0. Not equals to 1. Not equal to 0. That's a typo. probability, I guess I can write it as, well, anyway, let's leave it like that. So I could get rid of this, I guess. What they're saying is that if this is non-zero, this is a non-zero beta, you can put either a 1 or a 0 here. But if this is 0, then they want to make sure you get 0 here. So they call it weakly sparsistant. So it's a bit weaker than sparsistency. Here's the interesting thing. And let's take the dimension fixed. So this should be easier. Suppose I just did least squares. Because suppose the model was linear and I did least squares, and suppose the dimension was fixed. What do we expect beta hat minus beta to behave like? Well, we know that what we learned in 705 is that an estimator minus its true value is, what's the mean squared error like? It's like 1 over n, right? It's the bias, which would be, let's say 0, it's unbiased here, plus the variance. The variance is like some constant over n. But I'm adding up d things here. But I'm going to take d to be constant. So this is going to be, say, c over n. Or another way to say that is the expected value of n times beta hat minus beta squared will be constant. That's just estimating, ordinary estimation theory. What we're going to show now is that if your estimator is sparsistant, this goes to infinity. Okay? So that has a poor minimax risk. Infinite minimax risk, in fact. So here's the proof. It's very short. Let S be any vector in Rd. This is an arbitrary non-zero vector. Let's set beta sub n to be minus S over root n. So what I'm doing is taking something which is non-zero but close to 0. And that's the point. It's very hard to tell things that are 0 from things that are close to 0. So now watch what happens when I compute the maximum risk. The sup over all beta, the expected value under beta, of, I wrote this for a general loss function, but we're thinking here really what we usually use, right, is square root error loss. So let's look at this. There's our maximum risk, right? When we're doing minimax theory, we're taking the maximum over all betas. Well, the maximum over all betas is certainly bigger than or equal to the expected value at any particular beta. So I'm going to pick this particular beta. So that's bigger than or equal to the expected value under beta n of the loss okay. Now I'm going to say, well, that's bigger than or equal to. If I multiply that by an indicator function, it either leaves it alone or makes it 0. So it's bigger than or equal to that, right? So this is bigger than or equal to times the indicator that, so again, that's either 1 or 0, so it can't make it any bigger. Of course, now that we're on the event that beta hat's equal to 0, this is 0. So we have root n times minus beta n, and that cancels that. So I have the expected value. So this becomes, actually this becomes deterministic, right? This is just L of S, right? I'm just substituting beta equals to 0 in, and I'm substituting beta n equals to this, so that's just L of S, times the expected value of what's left over. Well, the indicator function, so that's actually just the probability. Okay. So let's actually write down what this is. So again, for squared error loss, this is just S squared. Well, it's actually the norm. It's the norm of S squared. Now here's the only tricky part. We're assuming sparsistency. What does that mean? That means if the truth is 0, the probability that beta hat is equal to 0 is going to 1. That's our assumption. That's the sparsistency assumption, or weak sparsistency assumption. That if it's truly 0, then eventually, with high probability, beta hat's going to be 0. This is the key. This is the sparsistency assumption. Now here's the only part that's non-obvious. If that's true under 0, what happens under beta sub n? Beta sub n is close to 0. So here I've swept a detail under the rug, which is you can prove that if this event happens with probability tending to 1, and because beta n is close to beta, this also converges to 1. This is called contiguity. So contiguity plays a big role in lots of areas of statistics. So I'm just going to say, if you want to look it up, we're not going to go into the details. You'll just have to take it on faith then. I hope that you'll trust me that this is going to 1. So this is converging to S squared. But S squared was arbitrary. I could take S to have norm bigger than any constant I want, let's say m. And that was arbitrary. So what we've just shown is that this risk is bigger than any constant m. Therefore, it's going to infinity. What is the implication for that? If you actually drew a picture of the risk function, what you would see is that away from 0, the risk could be quite small, and at 0, the risk could be quite small, but close to 0, the risk can really pop up and be big. So suppose this is 0. If I'm going to draw a risk function, it could look like this. The price of sparsistency is there are places in this parameter space close to 0 that have very, very large risk compared to, say, the least squares estimator. Now, does that mean you shouldn't use it? Not necessarily. It's just something to be aware of. That's all. And it's why you have to add assumptions like ruling those things out when you prove theorems about sparsistency and so on. So that's just something to think about, that there is a price to pay for being sparsistent. All right. So I think we can move on to classification. All right. It took longer than I thought. Just so you know, in the appendix of this, though, I talk about L2 boosting, for those of you who are interested in that. And I also have the proof of that greedy result, or at least most of the proof of that result. It's optional if you just want to look at it. So that's a quick review then of linear regression. Now we're going to do a quick review of linear classification. This I'm going to go even faster because you've all seen this between 701 or 715, 707. You've had your fill of linear classification. The only thing that I might surprise you with, if there's time, is remember I said there was a cool plot? Did any of you actually print out the cool plot? No one printed out the. Did anybody print out the cool plot? Nobody. Well, see, I told you there's a cool plot on the website. It's called Cool Plot, and it really is awesome what's going on there. But we'll see. We'll see. Didn't pique your curiosity. All right. So linear classification is very similar to linear regression. Like linear regression, when people use linear classification, obviously they don't usually necessarily assume that the best classifier is linear, but you're looking for, in some sense, the best linear classifier. And so, and I'm going to concentrate on the case where y is 0 or 1. And so a linear classifier would have the form 1 or 0, depending on whether and if life were simple, we would just look at the training error. Let's call this h beta. And we would say minimize that over all betas. That's the empirical risk minimizer. And there you go. You have a linear classifier. You just keep moving around a hyperplane until you minimize the number of mistakes you're making. You call that the empirical risk minimizer, and you'd be done. The difficulty is, as you know, is that that's a difficult minimization to do. It's not a nice, smooth minimization. So what are all the different ways we have of dealing with that? So I will remind you in a minute that if we could do the empirical risk minimization, how good is that classifier? We actually proved that in 705, but I'll remind you what the result is, right? That was all that VC stuff. But let me just first make a list of all the different ways I can think of getting linear classifiers, because empirical risk minimization certainly isn't the only one. So if we do, what's it called? Gaussian, make sure I use the same terminology that I used in the notes. Yeah, I guess, Gaussian discriminant analysis, or linear discriminant analysis, maybe. We'll quickly review each one if we need to, but remember that just corresponds to assuming you have two Gaussians and then estimating the parameters of the Gaussian. And then once you do that, you can estimate the optimal classifier, assuming the Gaussian assumption. And actually, let's just see if everybody remembers. Does that give you a linear classifier? If I just assume a Gaussian for the y equals to 0 and the Gaussian for the y equals to 1, and I find the optimal classifier, is that linear? No, it's quadratic, right? That's a quadratic. But if I assume the covariance functions are equal, then I get back the linear classifier. One of the best ones is logistic regression. Have you all seen that? Who has seen logistic regression? Who hasn't? Okay, so that doesn't add up to 1. Because I have to decide whether to review it or not. Well, anyway, maybe we'll review it very quickly. So logistic regression also gives a linear classifier. It's probably the most commonly used classifier in statistics profession. Would you agree with me? Yeah. I think in statistics that's the go-to guy. There's Fisher. I'll skip that one. There's support vector machines, which are just replacing this with a convex loss function, the hinge loss function. I think those are the most common linear classifiers. Am I missing any? I think those are the most commonly used linear classifiers. We do have a few minutes, so I can just quickly review them. Let's remind ourselves what the Bayes classifier is first. Remember, the Bayes classifier, the optimal classifier, let's call it H star, has smaller predictive risk than any other classifier, where H star is just 1 or 0 if the regression function is bigger than a half or less than a half, where mx or in other words, the mean of y given x. So that need not be linear, but we're going to use a linear classifier anyway, and we could try to do a modeling approach to try to get some sort of linear thing. And the Gaussian discriminant analysis and the logistic approach are just two different approaches to try to get the linear classifier from a modeling perspective. What's the difference? What's the key words there for Gaussian discrimination versus logistic? You all know it. It's discriminative versus generative, right? So if I think about writing down a model for y and x, I can factor this in two different ways. I could write it as f of x given y times f of y, or I could write it as and what's the difference? Well, if I start with this approach, if I specify a model for these things, I can now do maximum likelihood estimate the parameters of the model. Once I have the parameters of the model, I can estimate the mean of y given x, and I can estimate the Bayes rule. In this model, what's y? Y is 0, 1. So there's no model to specify there. It's just Bernoulli. Right? This is, if I write down the likelihood function, in fact, let's write out what this is. This is, let's call it pi. That's a product, and this is a parameter. So this part of the likelihood's easy. What's the MLE of pi? It's just the fraction of ones. Right. Here, we actually have to specify two densities, a density for x given y equals to 1, and a density for x given y equals 0. And so in the Gaussian discriminative case, we simply take them both to be Gaussian. So this would be Gaussian with a certain mean and variance. Now we have a fully specified model. It's called generative because I could actually generate new data this way. How would I do it? I would generate a y from this model and generate an x given y from this model. It's a fully specified model. Here it's Bernoulli. Here I just put in the normal and do the usual, maximum likelihood stuff and get mu hat and sigma hat. And it's easy once I have those to write down what the form of this rule is. What is the mean of y given x? In fact, it's all written down for you. It's all, you've seen it. Where is it written down? I forgot to do Hoofding. Let me come back to that in a minute. It's on page 7. It's just a formula involving the mu's and the sigmas. And as we just said a minute ago, if you really let sigma 1 and sigma 2, sigma 0 and sigma 1 be different, the corresponding decision rule is quadratic, so it's not a linear method anymore. But if you just force sigma 1 and sigma 0 to be equal, you get a linear separator. So I'm assuming you've seen this before, and if you need to remind yourself, the details are here. The other way, which is called discriminative, is to rewrite it this way. And why would we do that? Well, look, if I write it this way, what's the likelihood function? It's f of yi given xi times f of xi. And then I notice that to compute the optimal classifier, all I need is the mean of y given x. So if I've estimated this part of the distribution, I now have the classifier. I don't need this. So I can get away with modeling less in some sense. I only have to model the discriminative part of the distribution, not the rest. So in principle, the reason why some people prefer discriminative over generative is you say, well, we're actually modeling less. I'm being agnostic about the marginal distribution of x. I'm only modeling the distribution of y given x. Whether it really makes a difference in practice is another question, but at least philosophically, that seems like a good distinction. And in particular, so for the logistic approach, people assume the following model. It's understood again that no one thinks the model is true. It's just a way of getting out a classifier. And so basically, this is every yi conditional on xi is Bernoulli with this probability. Let's call this probability p of beta. And so now we just compute the likelihood function, which is a function of beta. It's p of beta to the yi and 1 minus p of beta to the 1 minus yi. This is a concave likelihood function, so it's very easy to maximize it. So you find beta hat. And now you've got what you want. Once you have beta hat, once you have the maximum likelihood estimator, our estimate of the regression function let me just call that beta, is right there. And now we just have to classify according to whether that's bigger than a half or less than a half. And again, it's easy to see that decision boundary is linear. In fact, here's an interesting fact that you would have learned in 701 or 715. This is linked to the Gaussian, right? if I started with the Gaussian assumption, and from the Gaussian assumption worked out what is the distribution of y given x, it's logistic. So that raises the following question. Am I doing the same thing when I do logistic regression? Let me say it again. I start with the Gaussian assumption. I say x given y is Gaussian, two different Gaussians. And now I just do the calculation. What's the mean of y given x? Or what's the distribution of y given x? The mean of y given x turns out to have this logistic form. These betas are going to be functions of the mu's and the sigmas. Does that mean if I do logistic regression and Gaussian discrimination, I'm getting the same classifier? No. Because even though they're mathematically related that way, when I actually go to optimize over the data, in the Gaussian case, I'm doing maximum likelihood and getting the mu hats and the sigma hats. In the logistic regression, I'm maximizing this likelihood function. It's a different criterion. So I'm going to get slightly different classifiers. And again, the people who prefer discriminated over generative would argue that this is a better thing to do because it's sort of modeling less in some sense. Although, again, I suspect in practice, I really doubt, I've never seen an example where there's a huge difference. Maybe that's just my experience. But philosophically, there actually is an interesting distinction between the two. And here's just a word of advice. Before you try, when you do any classification problem, before you try your favorite high-powered classifier and your deep whatever and your support vector machine, try logistic regression. Because it often works pretty well in a lot of problems. You don't need high-tech stuff all the time. Now, so I'm really running out of time, so I'm going to jump to a couple of last comments about this review. We can also regularize logistic regression. Here's our likelihood. So when I maximize the log likelihood, L is the log likelihood, little l is the log likelihood, you maximize that. If it's a high-dimensional problem, it's the same as linear regression. We can't just pretend that it's not high-dimensional. So we need a penalty, and you can just do exactly the same thing, except here I'm maximizing, so I guess I'll subtract the penalty. And so this would be sparse logistic regression. How do you do it? You know, actually, did I put the steps in? I think, yeah, we actually put there's different ways you could do this, and I don't know anything about optimization, so I'm just going to tell you. In the notes, I have a coordinate descent method. I have no idea whether that's a good idea or a bad idea. Take Ryan's course if you want to know how to do it properly. It's what's, I think, so by the way, you know, I don't think you're going to make them doing calculations, so they're like, do any computer code. So I'll say what I said in 705, which is, if there's any computing to do, I don't know if there will be. Use whatever you want, but you should use R. Because I know most of you will use MATLAB. But in R, I can tell you that the name of the function is, what's it called? What is it? No, that's not what it's called. Yeah, isn't it called GLMNet? This will do it in R. I'm sure there's something in MATLAB I don't know. Same thing. There you go. How about that? It's easy. So apparently I've lost the microphone. Where is it? It's just trailing around. How long has it been doing that?
I just noticed.
It's probably been like that all lecture, so you're going to have trouble hearing this lecture on the thing. I'm sorry about that. What happened was the clip fell off, and so I've been tying it around my button. Sorry about that.
You can put it inside your shirt and take it out. You're gonna hang there.
That's way too difficult. All right. I only have 3 minutes left. So, but fortunately, the last topic here is, again, something you covered in detail in 701 and 715. And we can return to it later if you think there's parts of it that were not covered in detail there, which is support vector machines. You know, actually, the truth is, starting that would be kind of crazy. So here's what we'll do. I also want, you know, I had a few let me say this. There's the support vector machine stuff. There's actually some interesting case studies here that I think are worth reading through, just because they compare different classifiers and so on. So you might want to take a look at that. There's the cool plot, which I haven't had time to explain. So we'll make a strategy decision on next Tuesday. Probably we'll just jump into non-parametric regression. I don't know that we need to go. You've all seen support vector machines, yes? Yeah. So this is just supposed to be reviewed, this chapter anyway. So all I'm going to say is just read through the rest of the chapter on your own. Make sure you remember this stuff. For the few of you who maybe have not seen a support vector machine, if you didn't have the prerequisites, just make sure you read through this section so you're familiar with it, because we're going to probably mention it several times in the course. So then watch, the homework's going to come out within the next few days, and then next week we're going to start non-parametric regression. Are the notes up yet, Ryan? So the notes will go up in a few days too for non-parametric regression. Sorry about the microphone. I hope it didn't fall down right at the beginning of class.